Hi, thanks for joining me today. I've got a fun Putnam problem for you. This comes from the 2010 Putnam and it's problem B1. We want to know, does there exist a sequence of real numbers an such that the sum from n equals 1 to infinity of an raised to the power of m equals m for all positive integers m? Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the solution to this problem is in fact quite short, and we're going to use a trick, and that trick's going to come from the Cauchy-Schwarz inequality. So what I've written down here is kind of a corollary of the Cauchy-Schwarz inequality, but you can kind of get a bit more of a general result. But if you've not heard of the Cauchy-Schwarz inequality before, I'll give you a chance to go ahead and look it up. But yeah, as I say, this is going to just be a corollary of the Cauchy-Schwarz inequality. So if we have sequences of real numbers bn and cn, then this inequality here holds. So that is the sum from n equals 1 to infinity of bn times cn all squared is going to be less than or equal to the sum of the bn squared times the sum of the cn squared. And I'm not going to prove this in this video, but as I say, it does just come directly from the Cauchy-Schwarz inequality. But what we're going to do is use this, and I claim that the sequence that we want to show, or we want to ask ourselves whether it exists or not, so the sequence of ANs, I claim that that does not exist, and we're going to prove that by using this inequality here. So suppose for contradiction that the sequence of ANs does exist. So that means that we have this AN such that A1 to the m plus A2 to the m plus so on off to infinity. This guy here equals m for all m. But then what we want to do is use our Cauchy-Schwarz inequality, and if we have a bit of a play around, we can actually just work with some low values for our index m, and if we just let bn just equal an for all n, and then cn to not equal an but to equal an squared for all n as well. Okay, then certainly bn and cn are going to be real sequences because an is a real sequence. And then if we just go ahead and plug that into our Cauchy-Schwarz inequality, that's going to tell us that the sum from n equals 1 to infinity of bn times cn, which is just an times an squared, which of course is an cubed, this guy here, all squared, is going to be less than or equal to, well, the sum of the bn squared, so the sum from n equals 1 to infinity of bn squared, well, bn is just an, so an squared, times the sum from n equals 1 to infinity of the cn squared. So the sum from n equals 1 to infinity of the cn squared, and that is just an squared squared, so an to the 4, like so. So we have this guy here. But then, well, we know that the sum from n equals 1 to infinity of an cubed, that's just going to be 3 from this line here, plugging in m equals 3. So on the left-hand side, we just have 3 squared, which is 9. And on the right-hand side, well, here we've got the sum from n equals 1 to infinity of an squared, which of course is just 2 from plugging in m equals 2 on this guy here. And then plugging in m equals 4 into this line here, we get the sum from n equals 1 to infinity of an to the 4 is just 4. So we get 9 is less than or equal to 2 times 4, which of course is 8. But clearly this is a contradiction, and that automatically solves our problem. So such an m, or such a sequence of ANs cannot exist, because if it did, then 9 would be less than or equal to 8, and that's certainly not true, and that solves our problem. I hope that has all made sense. It was a nice short video for you, I guess exemplifying that a lot of Putnam problems, once you get the nice trick, and the trick here was the Cauchy-Schwarz inequality, once you have that, the rest is usually just straightforward, or you know, it just comes quite nicely / quite elegantly. Anyway, I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.